So now we're going to take a second and go over some more application problems as well as review everything that's in this unit. So we started off with exponent rules. So that's simplifying your exponents. For example, x to the 4th squared would become x to the 8th. Okay, we had about 8 rules and we made a chart, so make sure you memorize that chart. Then we went into polynomial operations. Okay, remember a polynomial can have different number of terms. You have a monomial, a binomial, a trinomial, and then anything with 4 or more terms is just a polynomial. And we named them based on their highest exponent, that's the degree, and as well as we put them in descending order based on their exponents. That's how we write them in our standard form. So whenever we did our operations, we added, subtracted, and multiplied. And remember, multiplying, we had 2 options. One was FOIL and one was box. You just have to know one and get really good at it. You do not have to be able to do both. Then we went into graphing exponential functions. Remember our basic form. We have a times b to the x minus h plus k. A will tell us if it's reflected, right, if it goes down, and if it's bigger than 1, it's stretched, and if it's between 0 and 1, it is compressed, so it's flatter. Remember, we always do it vertically, so stretching makes it skinnier, compressing makes it flatter. B is our base. That always tells us whether it's growth or decay, so if B is bigger than 1, we have exponential growth, and if it's between 0 and 1, it's exponential decay. And then h and k are our transformations. So h is our horizontal transformation, and it's always important to keep in mind that it will always, always, always have the opposite sign. So if it's at x minus 1, that's really a positive 1, so it's going right 1. And then k has 2 jobs. It's our vertical translations as well as our asymptote, which is where our graph approaches but never touches. Okay, remember whenever you graph your exponential function, you make that table for whatever ab to the x is. And you use the same points, -2 to 2, make your table, plot them, and then apply your transformation left, right, up, or down. Okay, and then we looked at exponential applications, which we're going to do a couple problems now to continue what we worked on in class. So for the first one, in 2000, in 2000, the function modeling the U.S. population in millions was p equals 281 times 1.0124 to the t, where t is a number of years since 2000. And I don't like the way that went down, so I'm just going to add the equation here, just so we can see the whole equation at once. All right, so for part A, we want to know the population in 2000. Well, to start with, 2000 is 0 years from 2000. So if I plug in a 0, anything to the 0 power is 1, so it goes away, and I'm left with 281. So there were 281 million in 2000. Another thing to look at, or another way of looking at it, is it says in 2000 that this is our equation, and the 281 is the initial value, so in 2000 there are 281 million. Looking for the percent of increase, right? This is increasing, so that means we did 1 plus our rate to get 1.0124. So if I subtract 1, I get a decimal of 0.0124, so that's my rate. I move it over 2 to get my percent, so it's 1.24%. Then I want to know what the population will be in 2015. 2015 is 15 years away from 2000, so I'm just going to plug in 15 for t. And we can do this on the calculator. So let me pull up the calculator here. And I'm going to type it just like I see it. So we have 281 times 1.0124, and I'm going to use the caret button, 15. So we have 338.05, or we'll just round that to 338 million, or 338 million. And then I want to know when the population will be 400 million. Remember, anytime you're looking for when, that means you're looking for t in the equation, so I'm going to have to set it equal to something. So in this case, I'm going to set it equal to 400. And now I'm going to use the calculator to solve. And the way we do that is we cut it in half, and the left side we put in y1, the right side we put in y2. So in the calculator, I go to y equals, and I put 400. and then 281 times 1.0124, and then I'm going to use x as my variable. From here, I'm going to go straight to zoom 0 to see what the calculator can do. Remember, as long as your calculator is moving, it means it's thinking, it's processing. If you were to press a button, it would freeze and start shaking back and forth, and you think your calculator is broken. But it's not. It's just frozen. You paused it, so just press enter and it'll keep going. Slowly. Now I can see that here's my curve and it's coming up and it's not quite going to touch. My intersection's out here somewhere, so I'm going to zoom out. So zoom 3 and then press enter and see if that's enough to get me an intersection. Which it is, so now I go second trace down to number 5. And then the calculator is going to ask you those 3 questions, but with only 2 equations in, it can figure it out. So just press enter, enter, enter. And I want to know whatever the x value is. So in this case, 28.65, or we'll say 28.7 years. Number 2, a computer system valued at 6,500 depreciates at the rate of 14.3% per year. So depreciates means I'm going to use the 1 minus r equation, and then 14.3% is 0.143 as a decimal. So then my equation becomes A equals, and I start with $6,500, then I have 1 minus 0.143 to the t. Alright, and we can go a little farther and say that that is 6,500 times 0.857 to the t. Okay, and then I want to find the value after 3 years. So I'm just going to plug in 3 years to my time. So I would do 6,500 times 0.857 to the third, which I can go to my calculator, back to my home screen, and type it in just like I see it. So we get $4,091.25. And for the last one, I want to know when the system will be worth half its original value. So when means I'm looking for time, so I'm going to have to set up my equation. I'm going to set it equal to half the original value. Well, half of 6,500 is 3,250. So 3,250 equals 6,500 times 0.857 to the t. And this is one where we would go y1 and y2. And just to save us some time, I've already done this one, and so after 4.5 years, it'll be half the value. For the third one, a population of a certain animal species decreases at a rate of 3.5% each year. So decrease means I'm going to use subtraction. 3.5% becomes 0.035. So my equation becomes A equals, I start with 80. 1 minus 0.035 to the t, and we could simplify that one step farther, and it would become 0.965 to the t. Okay, for the second one, I want to know when the population will first drop below 15 animals. Now I want to know when, so that means I'm going to write one of those equations, and I'm going to set it equal to 15. And then I've got y1 and y2. So if I go to my calculator, in y1 I have 15, and 80 times 0.965 to the x. I'm going to go zoom 0 and let the calculator figure it out. Now, it wants to know when it will first drop below 15. That's the same thing as wanting to know when it gets to 15. So I'm still just going to be looking for my intersection. All right, now I can't really tell if it's intersecting here or not, and one way to find out if you can see your intersection is to go ahead and try to find the intersection. If your intersection can't be seen, you're going to get an error. Okay, but if it is in that window, your calculator will figure it out for you. So it looks like it's being able to calculate it, so it must be this bottom corner down here. error, no sign change, that means you can't see it. So that I'm going to quit, go back to my graph, go zoom 3. Let it load. Now I'm going to do the same thing again. This time I shouldn't get an error. There we go. So 46.98, or we can round that to 47. So this is 47 years. And the last one, how many animals remain after 10 years? I'm just going to plug in 10 for T. And I'll go back to my calculator, get out of my graph, and we have 80 times 0.965 to the 10th power. And we get 56. So we got about 56 animals after 10 years. And the last one we're going to do is actually number 6 on the worksheet from class, and it's Mr. Sawyer bought a condo for $175,000. The value will appreciate. Now, appreciate means it's increasing 6% per year. So 6% is 0.06. His plan is to live there until it's worth $250,000, then sell it and move. We want to know how many more years Mr. Sawyer needs to live in the condo if he sticks to his plan. So I want to know how many years. So I'm looking for time. So I'm going to write one of those equations where I have a left and a right side on the equal sign. So, that's our initial value times 1 plus 0.6 or 1.06 to the t, and I'm going to set that equal to 250,000. Have y1 and y2. So we have 250,000, 175,000 times 1.06 to the x. Zoom 0. Okay, and just going to go ahead and back out one time. That way I'm sure that the intersection's in there. Alright, second trace, number 5. Enter, enter, enter. And it's 6.1 years. So that's a pretty good investment if he only has to live there for 6 years and he can sell it for $250,000.